Ernest Lawrence started out his college education at the University of South Dakota, earning a bachelor's degree in chemistry in 1922. He then got his master's from the University of Minnesota and a PhD in physics from Yale University in 1925. After receiving his PhD, Lawrence spent 3 more years at Yale, the first 2 as a National Research Fellow and the third as an assistant professor of physics. He then moved to Berkeley, where he was appointed associate professor of physics and then professor 2 years later. He later moved on to be the director of the radiation lab in 1936. Ever since 1922, during his first year of graduate school, Lawrence was interested in generating high energies. However, no one knew how to generate the million volts necessary to penetrate the electrical barrier of the nucleus without electrical breakdown from sparking or overheating. Lawrence found the answer to this problem after many evenings spent researching in the library at Berkeley. In 1929, Lawrence studied the photos and diagrams in Wolf Woodrow's report titled "On a New Principle for the Production of Higher Voltages." This is where he got the ideas needed to construct the cyclotron. A current that rapidly changed from positive to negative potential could be used to push and pull positive ions, which would accelerate them. When he realized the acceleration tube would be too long, he came up with the idea of sending the positive ions back and forth through the electrodes in a spiral by putting it in a magnetic field. He soon discovered that in a magnetic field, slow particles completed their smaller circuits in the same time that faster particles completed their larger circuits, meaning that they could all be accelerated together.
The National Farm and Home Hour from the Berkeley campus of the University of California. But Dr. Lawrence, Henry's told us about all these new discoveries of yours with the 75 and the 225-ton cyclotrons. What do you need a great monster of 4,900 tons for?
Well, Jennings, you see, we've created valuable new substances and produced new forms of energy, well, such as the neutron ray, but we still can't completely smash an atom. For that, we need a 4,900-ton machine.
What's so important about smashing a little atom anyway?
Well, I think I can answer part of that, Jennings. For one thing, with the 4,900-ton cyclotron, it may be possible to change any element into another at will and then create valuable new substances to order. That would give us complete mastery over the physical world.
But there's even a greater goal, Henry.
Oh, you mean the release of atomic power?
That's right. You see, the nucleus of an atom makes up 99% of its weight, and within that nucleus is locked up a tremendous fund of energy.
And do you think that this 4,900-ton machine will be able to release it?
Well, Henry, according to our calculations, it will. Harnessing the atomic power will be another problem. But science has performed what seemed to be miracles before, and, well, I feel sure we will someday be able to put atomic power to practical use.
Well, that is a story.
Thanks for giving us your time, Dr. Lawrence.
Oh, not at all. Come back in 3 years, and I'll show you the new machine in operation.
That's the date. Goodbye, Dr. Lawrence.
Lawrence and his colleagues completed the first cyclotron in 1931. However, there were some complications. The effect was too weak to confine the higher speed particles. Lawrence's student, Stanley Livingston, figured that this was because of irregularities in the magnetic field. To fix this, Livingston used sheets of iron foil cut into a shape that Lawrence says was much like an exclamation point, and inserted it between the pole faces and the vacuum chamber. In February of 1932, the machine produced million-volt protons. Lawrence officially named it the cyclotron in 1936. In 1939, Ernest Lawrence was awarded the Nobel Prize in Physics. He went on to build larger and more powerful versions of the cyclotron. During World War II, he was very involved in the Manhattan Project, and his radiation lab became a major center for wartime atomic research. After World War II, Lawrence campaigned for large scientific programs. He was a member of the U.S. delegation at the 1958 Geneva Conference in trying to get an international agreement on the suspension of atomic bomb testing. He became sick while in Geneva and returned to Berkeley, dying a month later on August 27, 1958, at the age of 57.